of this chapter, of course, was on infinite series, but we weren't really concerned about finding the sums of these infinite series. We were just really concerned if these series converged or not. And we learned a lot of tests for a lot of different types of series, okay? And we're going to go ahead and put those, well, pun intended, to the test, all right? See if you know how to study convergence and divergence of series. So we got a few of them here. We got 6 that we're going to look at here. We're going to look and see if these series are convergent or divergent, okay? And we're going to actually go ahead and make sure that we actually state the theorems that we use, and we need to make sure that our conclusions are fully supported, okay? This is exactly how we're going to do it on the exam, okay? So let's take a look at this first one. We have n over n plus n squared over n plus n to the 4th. Now, you may be thinking to yourself, can I just divide out an n? Yeah, you certainly can, but let's leave it like this for a second, okay? Now, there are some rules of thumbs here, okay? Some ways that you can determine what test to use, okay? And in particular, let's take a look here. We have a rational function, okay? Polynomial or polynomial. It's bottom heavy. Let's go ahead and do some asymptotics, so to say, okay? Let's go ahead and look at the highest order terms here. If I were to take the limit here, and I want to think about like what terms would contribute into the limit. So we're going to go ahead and do this in the margin here, probably in pink here, all right? I'm going to make a note here that n plus n squared is going to behave more like n squared, okay? That little tilde just means asymptotic to, okay? Meaning in limits, as n gets large, it's going to behave more like the thing on the right. And in a similar fashion, n plus n to the 4th is asymptotic to n to the 4th. So I'm kind of going to go ahead and make a little guess here, okay, that our mystery series here, okay, at least the summands, we're going to have that n plus n squared over n plus n to the 4th is asymptotic to n squared over n to the 4th. Well, I can clean that up, right? It's n squared over n to the 4th. That's just 1 over n squared. And is 1 over n squared summable? You bet it is, okay? So we're going to go ahead and use limit comparison test against 1 over n squared. Okay, so now remember the limit comparison test. We're going to go ahead and take the limit of some ratio thingy here. All right. We're going to set it up like this. We'll have our mystery summands. So in the way that the theorem is phrased, these guys here, that's going to be your an, okay? And then, of course, the things in the pink, that's going to be the bn. Well, not in that pink, but, well, this pink. Okay, so we're going to look at the limits, okay, as n goes to infinity of an divided by bn, all right? Go back and look at the limit comparison test video, all right? So I'm going to go ahead and just write this down. So this is the limit as n goes to infinity of, well, I'm going to go ahead and do keep change flow because I don't like writing fraction over fraction. So we have the an bit, n plus n squared over n plus n to the 4th, multiplied by the reciprocal of the bn's, so we have n squared over 1. Okay, I'm going to go ahead and just multiply through in the top. So we have the limit as n goes to infinity of, well, n times n squared is n cubed, and then n squared times n squared is n to the 4th, divided by n plus n to the 4th. Okay, and just like I said in the first part of this video, you have a rational thing, just divide out by the highest power. Or if you're smart, you see that it's equal heavy, divide out by the leading coefficient to the highest power. Okay, in that sense, what you'll see is that this limit is 1. Okay, so the limit that we got was a positive finite number, okay? And so we know the following. As our reference series, okay, as our reference series converges, let's go ahead and make this make sense. As this reference series converges, our mystery series, okay, our unknown series converges by comparison. That's all there is to it, okay? So we use the limit comparison test here, okay? Remember, limit comparison test gives you a way to estimate the growth of this ratio, okay? And then it tells you that both series must behave the same. Now, you got to be a little careful if the limit is 0 or infinity. Technically speaking, in the analysis sense, you really got to work with something called the, if I remember right, it's the lim inf. I think it's either the lim inf or the lim sup. Doesn't really matter, but you got to handle those cases with the limit being 0 or infinity with some delicate care. All right, let's take a look at this next one here. We have an alternating series, okay, minus 1 to the n plus 1 times log n over n. Okay, this is an alternating series because we have a minus 1 to the n stuff. Okay, so we're going to go ahead and start with the alternating series test. Okay, we're going to start with the alternating series test here. We're going to set Bn, our helper sequence, equal to log of n over the square root of n. Okay, let's go ahead and highlight that in the same pink color here. That's going to be our helper sequence. Okay, now again, go back to the alternating series test video if you want the full hypotheses of the theorem, but basically what it says is, if our helper sequence is a positive decreasing sequence with limit 0, then the associated alternating series is convergent. Now, it only establishes convergence for the regular series, okay? But if we want to test for absolute convergence, we take absolute values, therefore discarding the minus 1 bits, and then we just use another test there, okay? For now, let's go ahead and just look at the alternating series test here. So I'm going to first go ahead and check if this thing is decreasing. This thing is certainly positive, okay? This thing is certainly positive, okay? I'll encourage you to check that, okay? Just remember how log is defined, okay, in our domain here, which is for n bigger than or equal to 1, okay? And so now we're going to go ahead and check for decreasing. And I'm actually going to do this by passing to a continuous function and taking a derivative. You'll kind of see why I'll be doing this in a second. So if I pass to a continuous function, and I look at log x over square root of x, and I take the derivative here, okay, we'll use the quotient rule. I'll spare the details here, okay, but think about it, right? Bottom times the derivative at the top, so square root of x over x, minus top times the derivative of the bottom. Okay, we'll get, let's see, log x over 2 square root of x, all over the bottom squared. Square root of x squared is just x. And if I pull out some common factors, actually, let me go ahead and simplify first up there. So square root of x divided by x gives me 1 over square root of x. I have log x over 2 square root of x. And I divide that by x. And now if I pull out some common factors and do a bit of fraction magic, I'll spare the details, but I encourage you to work out how this ends up being. Okay, we get 1 over x square root of x times 1 minus half of log x. Okay, so this is our derivative. And remember, for decreasing, okay, I'm going to put a note here in the margin. F is decreasing if the derivative is negative. So we need to check where this derivative is negative. Now, it only suffices to look at this stuff in green here. I only need to check where this thing is negative, okay? Because this thing, actually, let me go ahead and put that in another color, say red. This red stuff is always positive. Okay, this stuff is always positive for x bigger than 1. And why x bigger than 1? Because look at where our sum starts. Our sum starts at 1. So our starting point in our referential continuous part is going to be at 1. So we need, and I'll go ahead and put this in the same color, okay? We need, oh, that's obnoxious. We need to solve 1 minus 1/2 log x less than 0. Okay, this is an algebra exercise, okay? And I'll kind of spare the details here for you, but I'll talk through the steps here. Okay, if you shuffle some things over, okay, you'll get 2 is less than log x. Now you exponentiate both sides. Okay, you remember that e to the x is the inverse function of log x. We get e followed in x, okay, which says that x has to be bigger than e squared. X is bigger than e squared. That means that that thing in the green is negative. So that means that if that's negative, the derivative is negative, which means that the function is decreasing. All this to say, Bn is decreasing. So with the alternating series test, to check that the limit is 0, okay? And indeed it is, okay? We've done this limit many a time here. So the limit here, as n goes to infinity, of log of x over, log of n over square root of n. This is another L'Hopital's rule exercise, okay, of which I will spare the details here, okay, but this limit is 0. So I have a positive sequence that's decreasing with limits 0. What does that mean? That means that this sum, okay, the sum converges. Okay, so that sum converges. Now, I'm running out of room here, but you can actually end up, we don't even have to really do much more to show that this thing does not actually converge absolutely. Okay, this thing actually converges conditionally. And why is that? Because the integral test fails, okay? I'm going to go ahead and make a note here and use the integral test here. We already showed for the integral test part the decreasing bit, so we don't have to do that again. But when we look at the integral here of the absolute value of this thing, really just integrate log x over square root of x and do a change of variable. In fact, I'll probably go ahead and set it up here. Let's do this in red. Okay, if I integrate from 1 to infinity of log x over square root of x, okay, you have to use integration by parts here. Okay, you have to use integration by parts here. And in fact, the way that I did it is to first do a priming substitution by way of setting x equal e to the y, so that dx is equal to e to the y dy. Okay. And when I pass to the integral here, we will get, let's see, we get y times e to the y over 2 dy, and it doesn't take much to show that this is divergent, okay? But this integral diverges. Okay, I'll leave the details for you here. Okay, just for the sake of time and because I have run out of space. But right now we say that the sum converges conditionally, not absolutely. Okay, the sum converges conditionally, not absolutely. Now let's go ahead and look at a slightly easier one here. N squared over 3 to the n. I saw this one, I'm like, I already know for a fact this one converges. Okay, and the way that we're going to show convergence is by the ratio test. Okay, for the ratio test, okay, this is a special comparison against a geometric series. And so what we need to look at is we're going to look at the limit as n goes to infinity of an plus 1 over an, and that holding an absolute value. Okay, so to be kosher, I'll put down the absolute values here, although I don't need them because this is already a sequence of positive terms. So we'll have n plus 1 squared. Let's go ahead and fix that. N plus 1 squared divided by 3 to the n plus 1. Remember, we're replacing n with n plus 1. And then I'm going to multiply by the reciprocal just to make my life a little easier here. So 3 to the n over n squared. And now I'm just going to go ahead and clean up here. We see that I have a common 3 to the n here. So all I get left with is just a lone 3. So we have the limit as n goes to infinity of, and I'm going to go ahead and drop the absolute values because I can here. But actually, you know what? I'll just keep them in here just to be kosher. So we have 1/3, okay? 3 to the n divided by 3 to the n plus 1 is just 1/3. That's an exponent rule, okay? And then n plus 1 squared over n squared. Let's write that in real quick. We can use another exponent rule to combine these things. Okay, if I have powers, if I have an expression with the same, with stuff to an exponent, and the exponents are the same, and I have a product or quotient, I can put it into one big power. So I have n plus 1 over n squared. And this is where the magic happens here. After you do a bit of long division, well, not really long division, just how you add and subtract fractions, we get 1/3 here times 1 plus 1 over n squared. Okay, now note here that this thing here that I'm bracketing in blue, that thing goes to 0 as n gets large. Okay, it's easy to show. That thing goes to 0 as n goes to infinity. So in the end, the whole thing goes to 1/3. So as 1/3 is less than 1, the sum converges by the ratio test. Okay, so that one's done. Okay, very easy, right? Ratio test, super powerful, super nice to use. Now let's look at this one here. Square root of n minus 1 over n. This one I had to think about for a bit, and then I had a hunch here. Okay, let's go ahead in the margin. If we do that same kind of thing that I did in the last problem with the adding and subtracting of fractions, notice I can write this as square root of 1 minus 1 over n. Okay, that may help me a little bit, but also notice the following as well. This sort of almost looks like 1 over square root of n, right? If I discard the constant 1 there, okay, well, this thing here almost looks like a constant. I'm basically adding stuff that's going to be very, very close to 1. So I have a hunch that it diverges. Now, I kind of want to compare this using limit comparison. I want to compare this against 1 over n. Okay? And we know that 1 over n is not summable. Okay? This sum does not converge as p is equal to 1. Okay? So we're going to go ahead and do a limit comparison test against 1 over n. I think this is the most natural way of doing this. You can perhaps try a direct comparison. Notice here that we can't use the root test, okay? Root test means you take the terms and raise them to the 1 over n power. You take the nth root here. Here, that would just complicate things. So what we're going to do here is going to look at the limit as n goes to infinity. I'll go ahead and mark, okay, what we have here. So orange is the mystery. Orange is the mystery series. And pink is the reference series, okay? So we're going to go ahead and take this limit here, and I'm actually going to go ahead and fix this infinity here. So we're going to take the limit as n goes to infinity of, okay, square root of n minus 1 over n times the reciprocal of 1 over n, which is n. And now I'm going to go ahead and do a bit of magic here, okay? N is actually equal to the square root of n squared, okay? This is just to make some things work out nicer, okay? So I'm going to rewrite it like this. Square root of n minus 1 over n times the square root of n squared. And the square root is multiplicative, so I'm going to smash those two things under the same square root. And when I multiply, okay, n squared over n gives me an n. So in that square root, I'll get the square root of n times n minus 1, and alarm bell should be going off. That thing gets large, okay? That thing's going to behave like n. If you discard, well, if you multiply it out, you get n squared minus n in the square root, and that's going to behave like square root of n squared, which we just said is n. So this thing goes to infinity, okay? Now, for the limit comparison test, we have the special case of the infinity case here, okay? But this sum, 1 over n, is divergent. So, by LCT, by the limit comparison test, our mystery series diverges as well. All right. So that's a nice use of the limit comparison test. There may be another solution here, but I found that this was probably the more natural one. Okay, remember, for limit comparison tests, it's enough to compare against like probably the best thing, but you can find other things to compare against, so long as you know that it should behave the same as the reference in the mystery. All right, this one here I really like here. Sine of n over 1 plus n squared. We're going to do something a little more powerful here. Let's test for absolute convergence. Let's test for absolute convergence. Okay, so we're going to test for absolute convergence. So here's what we're going to do, okay? Now, for absolute convergence, we're going to do the following. Okay, we're going to note, as in the previous video, that the sine of n, sine of x, is going to be less than or equal to 1 in absolute value. Okay, so what we're actually going to do is use this inequality here. Okay, so we're actually going to use the direct comparison test. That is actually going to tell us something very, very powerful. All right, so here's how the direct comparison is going to go. We're going to take the absolute value of our summand, sine of n over 1 plus n squared. Now, by properties of absolute value, okay, absolute value is multiplicative, so I can take the absolute value at the top divided by the absolute value at the bottom. So the sine of n, as we said there, is less than or equal to 1 in absolute value. That's way too close. And then on the bottom, okay, we'll still keep it as a 1 plus n squared. Okay, 1 plus n squared, okay? It's positive already, so we can drop the absolute values. Okay, well, what does that really give me? Okay, now let's think about this comparison as well. Can I improve this estimate a bit further? Well, let's remember here, okay? If I make the denominator of a fraction smaller, I make the fraction bigger. So if I have the following here, if x is smaller than y, then by taking reciprocals, I have that 1 over x is greater than 1 over y. Okay, taking reciprocals flips the things. Okay, and in particular, what does this tell us? N squared is certainly smaller than n squared plus 1. Now, when I take reciprocals, 1 over n squared plus 1 is smaller than 1 over n squared. And so I can use that comparison. 1 over n squared. Now, why did I do that? Because this thing here, at the end here, which I'll highlight in, what's the color we haven't used here, this light blue here. This thing here, okay. So as this thing here, okay, as the blue blob, okay, corresponds to a p-series with p bigger than 1, here p is equal to 2, okay. The sum is convergent, and in this case, we've got a little more powerful. Absolutely. By the direct comparison test. Now, why do we get absolute convergence out of this? Because I took the sum of the absolute values, okay? If I can compare the sum of the absolute values of something, I'm in good shape. All right, we're on to this last one here. 1 over n times the square of log n. If it looks very complicated, you may want to use the integral test here. And I already have a feeling I want to use the integral test here. All right, so let's use the integral test here. Okay, for the integral test, we have to verify that we have a positive function that's decreasing, okay, and then we just convert to an improper integral. Okay, I'll go ahead and claim that this thing is already positive. I won't show that. That's easy to show, but it's positive. But we're going to pass this to a continuous function. So we'll first check the derivative of this thing, 1 over x times log of x squared. And you can show by some work, so you do a bit of work here, do some calculus 1 knowledge, you get, let's look at the notes here. A lot of stuff. You can show that the derivative is minus, oh boy, x times log of x squared times 2 log x plus log of x squared. Okay, so I'm going to spare you the details for real this time. So we need to show that this is negative, okay? Now, we already have some cool things here. This term here, because we have a square, and we're multiplying by a number that's bigger than 0 anyway, positive times positive is positive. So this thing is already positive. Okay, that's fine. But now we got to look at the rest of it, the negative stuff. Let's go ahead and bracket that in this blue color. So is this blue stuff negative? Well, we have a negative sign, so it suffices to check. It suffices to check if 2 log x plus the square of log x is positive. Because if that's positive, they want to multiply by -1, it's negative. Now, this actually works out really nicely, okay? This is actually a quadratic in log of x, okay? So if I factor out a common log of x, so we have log of x times 2 plus log of x, that's going to be greater than 0. Okay, now go ahead and remember like some of your basic things with these inequalities here, okay? The signs have to match, so those have to be positive, okay? So certainly here, we can show that indeed for, let's see here. Okay, we can actually show that this is positive for all x greater than 0. Nope, sorry. for all x greater than e at least, that indeed works. And this is indeed true for all x greater than e. And so we can show by some arguments that this function, okay, this guy is decreasing. So the integral test applies. Okay, now for the integral test, okay, again, we just go ahead and take the integral. So we'll have 1 over x times log of x squared dx. Okay, that's an improper integral. Okay, so we need to take the limit here as t goes to infinity of 2, okay, integral from 2 to t of 1 over x log of x. There we go, squared dx. Okay, by a simple u substitution, which I'll omit for the moment, okay, we can show log of x here. Let's go over here. Just feel this gear. Okay. And you can in fact show that this thing converges. We get a limit of 1 over log 2. And so, because the improper integral converges, this thing converges. So let's go ahead and put that here. Okay, so that was a whirlwind tour of a lot of the series tests that we use. Okay, it wasn't all of them, but it was a good chunk of them. Okay, the next one, we're actually going to do certain sums of series. Okay, so no tests no more. We're actually going to evaluate some sums of series. And for that, I will see you in the next one.